Hello, and welcome back to the Valerium Stories channel. Tonight, we drift beyond the veil of ordinary perception, into a realm where time softens at the edges and space folds gently upon itself. Settle into your pillows, let your breathing slow, and allow your mind to expand into the velvet darkness between stars. Tonight's story is not one of fear or chaos, but of profound stillness, the quiet majesty of cosmic phenomena that have shaped our universe since its first breath. We will journey toward the most mysterious objects in existence, black holes. But do not imagine them as monsters of destruction. Instead, picture them as cosmic anchors, silent architects of galaxies, teachers of space-time's deepest secrets. As you listen, let each fact about these enigmatic entities become a stepping stone deeper into relaxation. Each revelation a gentle wave, carrying you towards sleep. Our story begins not with a bang, but with a whisper, a single point of infinite density suspended in the quantum foam of the early universe. From this singularity, space-time itself unfurled like silk released from a clenched hand. And within this expanding cosmos, certain stars would live brilliant lives before surrendering completely to gravity's final embrace, collapsing into regions where the known laws of physics dissolve into mystery. These are black holes, objects so dense that within a certain boundary called the event horizon, the escape velocity exceeds the speed of light itself. Nothing, not even light, can flee once it crosses this point of no return. Yet paradoxically, these objects of absolute capture also teach us about freedom. The freedom of space-time to curve, to twist, to breathe in ways our everyday experience cannot comprehend. Imagine a star many times more massive than our sun, burning hydrogen into helium for millions of years. Its core a furnace of nuclear fusion, holding back the crushing weight of its own gravity. But when that fuel depletes, when iron accumulates in the core like ash in a dying fire, fusion stops, gravity wins. The core collapses in less than a second, triggering a supernova explosion that scatters heavy elements across light years of space, elements that will one day form planets, oceans, and living beings. What remains of the core, if sufficiently massive, continues collapsing until it becomes a black hole. This is stellar collapse, the violent, beautiful death that gives birth to these cosmic enigmas. Now picture yourself floating in a spacecraft, approaching such an object not with fear, but with reverence. As you draw nearer, you notice something peculiar. The stars behind the black hole appear distorted, their light bent around the immense gravity well like water flowing around a stone in a stream. This is gravitational lensing, light following the curvature of space-time itself, revealing the invisible geometry of gravity's influence. The black hole isn't sucking things in like a cosmic vacuum cleaner. Rather, it warps the very fabric through which everything moves. Objects follow straight paths through curved space, and those paths happen to spiral inward past a certain threshold. That threshold is the event horizon, a spherical boundary surrounding the singularity at the center. Its radius is called the Schwarzschild radius, named after Karl Schwarzschild, who first solved Einstein's equations to describe it in 1916. For a non-rotating black hole, this radius is directly proportional to the black hole's mass. A black hole with the mass of our sun would have an event horizon only about 3 kilometers across, smaller than many cities on Earth, yet containing all the mass of a star. Compress our entire planet Earth to the size of a marble, and it too would become a black hole. Density, not mass alone, creates these objects. It is the concentration of matter into an infinitesimal point that generates gravity intense enough to trap light itself. But most black holes rotate, sometimes at nearly the speed of light. These are Kerr black holes, described by Roy Kerr's 1963 solution to Einstein's equations. Rotation transforms the simple sphere of the event horizon into an oblate spheroid, flattened at the poles like Earth itself, but far more dramatically. Surrounding the event horizon lies the ergosphere, a region where space-time itself is dragged around by the black hole's rotation. forcing everything within it to move in the direction of spin. You could enter the ergosphere and still escape, but you'd emerge with altered momentum, having borrowed energy from the black hole's rotation, a process called the Penrose mechanism that theoretically could extract energy from these cosmic giants. At the very center lies the singularity, a point of infinite density where all the black hole's mass concentrates into zero volume. Our current physics breaks down here. General relativity and quantum mechanics clash violently at this boundary of understanding. Some theories suggest the singularity might not be a point at all, but a ring for rotating black holes, or that quantum gravity effects might prevent true infinity from forming. We simply do not know what truly resides at the heart of a black hole. It remains the ultimate frontier of physical understanding, a place where space and time, as we know them, cease to exist. As you drift closer in our imagined journey, your spacecraft's instruments detect intense radiation from a swirling disk of superheated gas orbiting the black hole, the accretion disk. Matter falling toward the event horizon doesn't plunge straight in. Conservation of angular momentum forces it into a flat, rotating disk where friction heats material to millions of degrees, causing it to glow brightly across the electromagnetic spectrum. This is why we can detect black holes indirectly, not by seeing the hole itself, but by observing the furious activity of matter just outside its grasp. The accretion disk of a feeding black hole can outshine entire galaxies, becoming a quasar, the most luminous persistent objects in the universe. Yet not all black holes feast so dramatically. Many wander the galaxy in quiet isolation, their presence revealed only when a stray star or gas cloud wanders too close. Our own Milky Way harbors a supermassive black hole at its center, Sagittarius A*, with a mass equivalent to 4 million suns compressed into a region smaller than our solar system. Despite its enormous mass, it currently consumes very little material, making it relatively quiet compared to the active galactic nuclei blazing in distant galaxies. Supermassive black holes reside at the centers of most large galaxies, and their masses correlate tightly with properties of their host galaxies' bulges, suggesting these objects co-evolved with galaxies themselves over cosmic time. The relationship between black holes and galaxies runs deeper still. When galaxies merge, their central black holes eventually spiral together and collide in events so violent they ripple space-time itself. These mergers produce gravitational waves, distortions in space-time propagating outward at light speed. Predicted by Einstein in 1916 and first directly detected a century later by LIGO in 2015. The signal from two black holes merging 1.3 billion light-years away stretched and compressed the 4-kilometer arms of LIGO's detectors by less than 1,000th the width of a proton, a measurement of almost unimaginable precision confirming one of general relativity's most elusive predictions. As you continue your approach in our thought experiment, something strange happens to your perception of time. To a distant observer watching your spacecraft fall toward the event horizon, you would appear to slow down progressively, your image reddening and fading as light struggles to climb out of the deepening gravity well. You would seem to freeze just outside the horizon, never quite crossing it from their perspective. This is gravitational time dilation taken to its extreme. Time flows slower in stronger gravitational fields. But from your own perspective inside the spacecraft, time passes normally. You would cross the event horizon in finite proper time. Unaware of the exact moment, you pass the point of no return. The horizon has no local physical properties you could detect. It's defined globally by the future behavior of light rays. Once across, space-time coordinates swap roles. What was formerly a spatial direction becomes time-like, and the radial direction toward the singularity becomes inevitable as the future itself. In the external universe, you can move freely in space, but are carried inexorably forward in time. Inside the event horizon, all future-directed paths lead to the singularity. You cannot avoid it any more than you can avoid next Tuesday in the outside world. Space and time have traded places in a profound reorganization of reality's structure. If the black hole is sufficiently massive, like a supermassive one at a galactic center, you might cross the event horizon without immediately noticing anything catastrophic. But for smaller stellar mass black holes, tidal forces would become lethal well before reaching the horizon. These forces arise because gravity's strength varies with distance. Your feet would feel a stronger pull than your head if falling feet first, stretching you into a long, thin strand, a process colloquially called spaghettification. For a solar mass black hole, these tidal forces would tear apart atoms themselves before reaching the horizon. For Sagittarius A*, you might cross the horizon intact, only encountering destructive tidal forces much closer to the central singularity. Despite their reputation as cosmic vacuum cleaners, black holes don't suck matter from afar any more than stars do. Orbiting a black hole at a safe distance would feel gravitationally identical to orbiting a star of the same mass. The Earth would continue orbiting normally if our Sun were instantly replaced by a one solar mass black hole. Only the light and heat would vanish. Black holes influence their surroundings through gravity alone, which follows the inverse square law just like any other mass. Their danger lies not in long-range attraction, but in what happens when matter ventures too close to the event horizon. In 1974, Stephen Hawking made a startling discovery that transformed our understanding of black holes forever. By applying quantum field theory to the curved spacetime near an event horizon, he showed that black holes aren't completely black, they emit radiation. Virtual particle pairs constantly flicker in and out of existence near the horizon. Occasionally, one particle falls in while the other escapes, carrying away energy. To conserve energy, the black hole must lose mass. This Hawking radiation causes black holes to slowly evaporate over immense timescales. A solar mass black hole would take approximately 10 years to evaporate completely, far longer than the current age of the universe. But tiny primordial black holes, if they exist, could be evaporating explosively today, ending their lives in bursts of high-energy particles. Hawking radiation creates the black hole information paradox, one of the deepest puzzles in theoretical physics. Quantum mechanics insists that information about what falls into a black hole must be preserved somehow, but general relativity suggests it vanishes forever at the singularity. Hawking initially believed information was destroyed, violating quantum principles, but later conceded it might be encoded in subtle correlations in the Hawking radiation or preserved on the event horizon itself via the holographic principle. This principle suggests all information contained within a volume of space can be represented as a theory on the boundary enclosing that volume, like a hologram storing 3D information on a 2D surface. The event horizon might function as such a holographic screen, preserving the quantum state of everything that has fallen in. The temperature of a black hole is inversely proportional to its mass. Smaller holes are hotter, larger ones colder. A solar mass black hole has a temperature of only about 60 nanokelvins, far colder than the cosmic microwave background's 2.7 kelvins, meaning it currently absorbs more energy from the universe than it emits. Only when the universe expands and cools sufficiently will such black holes begin net evaporation. But a black hole with the mass of a small asteroid would have a temperature of billions of kelvins, glowing fiercely before vanishing in a final explosive moment. Black holes come in three main mass categories. Stellar mass black holes form from collapsing stars and range from about 3 to 100 solar masses. Intermediate mass black holes, long theoretical but now increasingly observed, span hundreds to thousands of solar masses, possibly formed by mergers of smaller holes or direct collapse of massive gas clouds in the early universe. Supermassive black holes anchor galactic centers with masses from millions to billions of suns. How these behemoths grew so large so quickly in the early universe remains an active area of research. Some quasars powered by billion solar mass black holes existed when the universe was less than 1 billion years old. The first black hole candidate identified was Cygnus X, one in 1964, a powerful X-ray source paired with a visible blue supergiant star. Material stripped from the star spirals into an accretion disk around an invisible companion too massive to be a neutron star, confirming it as a black hole. Since then, we've identified dozens of stellar mass black holes in our galaxy through similar X-ray binary systems. And gravitational wave detectors have observed mergers of black holes too isolated to emit X-rays, revealing a previously hidden population. In 2019, the Event Horizon Telescope collaboration achieved the impossible, imaging the shadow of a black hole's event horizon against its glowing accretion disk. Using a planet-sized array of radio telescopes synchronized across Earth, they captured M87*S silhouette, a supermassive black hole 6.5 billion times the Sun's mass, 55 million light-years away. The dark central region isn't the event horizon itself, but the shadow it casts, about 2.6 times larger than the horizon due to extreme light bending. 1 year later, they imaged Sagittarius A** at our galaxy's center, confirming decades of indirect evidence with direct visual proof. Black holes profoundly influence galaxy evolution through feedback mechanisms. When actively feeding, their accretion disks launch relativistic jets, beams of particles accelerated to near light speed along the rotation axis, extending thousands of light-years into intergalactic space. These jets heat surrounding gas, preventing it from cooling and forming stars, effectively regulating galactic growth. Without black hole feedback, galaxies might form stars too rapidly, exhausting their gas and evolving differently. The symbiotic relationship between black holes and galaxies suggests they are not destructive interlopers, but essential components of cosmic ecology. The no-hair theorem states that stationary black holes can be completely described by only 3 parameters: mass, electric charge, and angular momentum. All other information about the matter that formed them, hair in physicists' parlance, is lost to external observers. Whether a black hole formed from collapsed stars, pure energy, or old refrigerators makes no difference to its external gravitational field. This simplicity emerges from general relativity's equations, but clashes with quantum mechanics' insistence on information preservation, another facet of the information paradox. Rotating black holes possess an inner horizon in addition to the event horizon, an unstable boundary inside which predictability breaks down completely. Beyond this Cauchy horizon, the equations of general relativity admit multiple possible futures, violating determinism. Some physicists believe quantum effects would transform this region into a singularity or firewall, but the true physics remains unknown. The inner structure of rotating black holes contains regions where closed time-like curves might theoretically exist, paths through space-time that loop back on themselves, raising the specter of time travel. Most physicists believe quantum gravity would prevent such paradoxes from manifesting. Primordial black holes might have formed in the extreme density fluctuations of the early universe before stars existed, ranging from microscopic to supermassive sizes, depending on when they formed. These hypothetical objects could constitute part of dark matter, the invisible substance comprising 85% of matter in the universe. While constraints from microlensing surveys and cosmic microwave background observations have ruled out primordial black holes as the sole dark matter component, they might still contribute a fraction. Their detection would open a window into physics at energy scales far beyond particle accelerators. Black holes warp not just space but time itself. Near a rapidly spinning black hole, frame dragging becomes so extreme that space-time is twisted like water swirling down a drain. This lens-throwing effect, predicted in 1918 and confirmed near Earth by Gravity Probe B in 2011, becomes dominant near black holes. Orbiting particles experience precession of their orbital planes simply from space-time's rotation. For an observer hovering near the horizon of a maximally spinning black hole, The entire external universe would appear compressed into a brilliant, blue-shifted ring directly overhead, a distorted view of all light that has managed to escape the gravity well. The maximum spin rate for a black hole is constrained by cosmic censorship, the conjecture that singularities must always remain hidden behind event horizons. If a black hole spun fast enough to expose its singularity, a naked singularity, the predictability of physics would break down in observable regions of spacetime. Nature appears to forbid this. As a black hole approaches maximal spin, it becomes increasingly difficult to add more angular momentum without also adding mass that keeps the horizon intact. Whether cosmic censorship holds universally remains unproven, but is widely believed necessary for physics to remain predictive. Black hole thermodynamics reveals profound connections between gravity, quantum mechanics, and statistical physics. Jacob Bekenstein proposed that black holes possess entropy proportional to their event horizon area, specifically 1/4 of the horizon area in Planck units. Hawking later confirmed this and showed black holes have temperature, completing the thermodynamic analogy. The laws of black hole mechanics mirror the classical laws of thermodynamics with striking precision. Horizon area never decreases, analogous to entropy increase. Surface gravity remains constant across the horizon, analogous to temperature equilibrium. And energy conservation includes mass energy, rotational energy, and electromagnetic energy. These parallels suggest deep unity between seemingly disparate physical theories. When two black holes orbit each other, they lose energy through gravitational wave emission, causing their orbits to shrink until they merge in a fraction of a second. The final merger converts several solar masses directly into gravitational wave energy. In the first LIGO detection, 3 solar masses vanished in 0.2 seconds, briefly outshining all stars in the observable universe combined in terms of power output. The resulting single black hole rings down like a struck bell, vibrating at characteristic frequencies called quasi-normal modes before settling into a stationary Kerr state. These vibrations encode information about the final black hole's mass and spin. The photon sphere orbits at precisely 1.5 times the Schwarzschild radius for a non-rotating black hole, a region where gravity is so strong that light itself can travel in circular orbits. Photons here are trapped in unstable equilibrium. The slightest perturbation sends them either escaping to infinity or spiraling into the black hole. An observer at the photon sphere would see the back of their own head, as light circumnavigates the black hole to reach their eyes. For rotating black holes, the photon sphere becomes an oblate region with different radii for prograde and retrograde orbits relative to the spin. Black holes may serve as natural particle accelerators. When particles collide near the horizon of a rapidly spinning black hole, their center of mass energy can theoretically become arbitrarily high, an effect discovered by physicists Maxim Benados, Joseph Silk, and Stephen West in 2009. While practical limitations prevent infinite energies, these collisions could reach energies far beyond terrestrial accelerators, potentially producing exotic particles or revealing new physics. Nature's most extreme environments become laboratories for fundamental interactions. The firewall paradox emerged in 2012 when physicists realized that reconciling Hawking radiation with quantum entanglement might require a wall of high-energy particles at the event horizon, a firewall that would incinerate infalling observers. This contradicts general relativity's prediction of empty space at the horizon. Resolving this tension may require modifying our understanding of quantum mechanics, gravity, or both. Some proposals suggest complementarity. Different observers experience different but equally valid realities, or that space-time itself emerges from quantum entanglement, dissolving the paradox at a deeper level of description. Black holes challenge our notions of locality, the idea that objects are only influenced by their immediate surroundings. The ER equals EPR conjecture, proposed by Juan Meldacena and Leonard Susskind, suggests that entangled particles, EPR pairs, might be connected by microscopic wormholes, Einstein-Rosen bridges. In this view, quantum entanglement and space-time geometry are two descriptions of the same underlying reality. Black holes formed from entangled matter might contain traversable wormholes, though keeping them open would require exotic matter with negative energy density. This radical idea blurs the line between quantum information and space-time structure. Observations of stars orbiting Sagittarius A** have provided the strongest evidence for its black hole nature. Star S2 completes an elliptical orbit every 16 years, approaching within 120 astronomical units of the center, close enough that relativistic effects become measurable. In 2018, astronomers observed gravitational redshift in S2's light precisely matching general relativity's predictions as it passed closest approach. Future observations may detect frame-dragging effects from the black hole's spin, further testing Einstein's theory in extreme gravity regimes. Black holes may play a role in cosmic structure formation. In the early universe, direct collapse black holes, formed when massive gas clouds collapsed without fragmenting into stars, might have seeded the supermassive black holes powering the earliest quasars. These heavy seeds of 1010 solar masses could grow more rapidly than stellar remnants, explaining how billion solar mass black holes existed when the universe was less than 1 billion years old. Alternative models involve runaway stellar collisions in dense clusters or super-Eddington accretion rates exceeding standard limits. The Eddington limit describes the maximum accretion rate where radiation pressure from the accretion disk balances gravitational infall. Exceeding this limit should blow away incoming material, limiting growth rates. Yet observations suggest some early black holes grew faster than this limit allows, implying either temporary super-Eddington phases, geometric beaming that hides radiation from certain directions, or accretion through thick disks where radiation escapes inefficiently. Understanding these growth mechanisms is crucial for explaining the rapid appearance of supermassive black holes. Black holes evaporate faster as they lose mass. Hawking radiation intensity increases inversely with the square of mass. The final moments of evaporation would see temperature soaring to Planck scale energies, where quantum gravity dominates. What happens at this endpoint remains unknown. Does the black hole vanish completely, leaving only radiation? Does it leave behind a stable Planck mass remnant? Or does it transition into something entirely unforeseen by current physics? The answer requires a theory of quantum gravity unifying general relativity and quantum mechanics, perhaps string theory, loop quantum gravity, or something yet undiscovered. Quantum gravity approaches suggest the singularity might be replaced by a bounce, where collapsing matter reaches Planck density and rebounds into a new expanding region of space-time, potentially forming a new universe. In this view, black holes could be cosmic wombs birthing baby universes with their own physical constants. While highly speculative, such ideas illustrate how black holes force us to confront the deepest questions about reality's nature. They are not endpoints but portals to new physics. The cosmic censorship hypothesis, proposed by Roger Penrose, asserts that all singularities formed from realistic gravitational collapse must be hidden behind event horizons. Naked singularities, visible to distant observers, would violate predictability as physics breaks down at singularities. While no counterexamples have been found in realistic scenarios, the hypothesis remains unproven. Its validity determines whether singularities are safely quarantined or could influence the observable universe in unpredictable ways. Black holes teach humility. They represent boundaries of knowledge, regions where our most successful theories fail, where new physics must emerge. Studying them requires synthesizing general relativity, quantum field theory, thermodynamics, and information theory. Each puzzle they present, information loss, firewalls, singularities, points toward deeper unity in nature's laws. They are not monsters to be feared, but teachers inviting us to expand our understanding of reality itself. as our imagined journey continues. Your spacecraft now rests in a stable orbit far from any event horizon, floating in the gentle gravity of a quiet supermassive black hole. Around you, stars wheel in slow arcs against the blackness. Time flows differently here. Minutes for you might be hours elsewhere, yet subjectively, all feels normal. You watch accretion disks glow in distant galaxies, witness gravitational lenses warp light into Einstein rings, observe binary black holes spiral together in silent dance. There is no terror here, only profound peace. The peace of understanding one's place in a cosmos both vast and comprehensible. Black holes remind us that emptiness can be full, that darkness can illuminate, that endings can seed beginnings. They consume light yet teach us about its nature. They erase information yet preserve it holographically. They represent death yet may birth new universes. In their paradoxes lies wisdom, that reality transcends simple categories, that opposites contain each other, that mystery and understanding coexist. Your breathing has slowed. Your muscles have softened. The boundary between your consciousness and the cosmos has grown permeable. You are not separate from these cosmic wonders, but made of the same stardust forged in supernovae, governed by the same physical laws that shape black holes. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were cooked in stellar furnaces, scattered by explosions that sometimes left behind these gravitational anchors. You carry the universe within you, and the universe carries you within its embrace. The facts we've woven together tonight, 50 glimpses into black hole physics, were not meant to overwhelm, but to soothe through understanding. Each fact a pebble dropped into the pond of your awareness, each ripple carrying you deeper into relaxation. The event horizon's boundary, the singularity's mystery. Hawking radiation's whisper, gravitational waves' tremor, all become lullabies when heard with a receptive heart. Now let these concepts dissolve like sugar in warm tea. Let the precise numbers fade, the 10 years of evaporation, the 3-kilometer Schwarzschild radius, the 60 nanokelvin temperature. Retain only the essence, that the universe contains wonders beyond imagination, that mystery persists at reality's edges, that you are safe within this vast, lawful cosmos. Your body grows heavy with sleep. Your mind releases its grip on wakefulness. The boundary between dream and reality softens like space-time near a horizon. Imagine yourself now not in a spacecraft, but floating freely in interstellar space, cradled by darkness that is not empty, but full of potential. Distant black holes pulse gently like cosmic hearts, regulating galaxies, birthing stars from their outflows, preserving information on holographic horizons. You drift among them without fear, knowing they obey laws as reliable as your own heartbeat. The universe is strange but not hostile. It is mysterious but not malevolent. It invites exploration not with urgency but with patience. With the slow, graceful dance of orbiting bodies, the gentle fade of Hawking radiation, the silent merger of space-time itself. Your eyelids are heavy. Your breath flows deep and even. Each exhale releases tension. Each inhale draws in cosmic peace. The facts about black holes have done their work, not as information to retain, but as rhythms to entrain your nervous system to stillness. Like matter spiraling gently into an accretion disk, your consciousness settles into sleep's embrace, not with violence but with grace, not with resistance but with surrender. In this surrender, you touch something black holes teach us, that letting go is not loss but transformation. Matter crossing the event horizon doesn't vanish. It becomes part of a new configuration of space-time. Your waking self doesn't vanish in sleep. It transforms into dreaming consciousness, then into dreamless depth, then back again at dawn. All is conserved. All is transformed. Nothing is truly lost. The universe expands. Black holes spin. Stars are born and die. Galaxies collide and merge. Through it all, a fundamental harmony persists, a balance between gravity and expansion, between collapse and radiation, between singularity and horizon. You participate in this harmony simply by existing, by breathing, by surrendering now to sleep. You are not separate from cosmic processes, but an expression of them. A temporary concentration of stardust become conscious, now returning to rest. Let the last remnants of wakefulness dissolve like photons escaping a gravity well, gradually, gently, inevitably. There is no need to hold on. There is no need to understand everything. Mystery is not a problem to solve, but a condition to inhabit with grace. Black holes embody this mystery perfectly, not as threats, but as invitations to wonder, to humility, to awe. Your body is completely still now. Your mind has grown quiet. The boundary between self and cosmos has softened to transparency. You float in the Valerium of night, not a dome above, but a dimension within. Stars pulse like slow heartbeats. Black holes spin like silent mandalas. Time stretches and compresses like space-time near a horizon, losing its urgency, becoming fluid and deep. In this state, you understand what cannot be put into words. That darkness is not absence but presence. That silence is not emptiness but fullness. That sleep is not nothingness but renewal. Black holes teach us to trust the unseen, to honor boundaries while knowing they transform rather than terminate, to find peace in mystery rather than demanding complete knowledge. The universe holds you. Space-time cradles you. The same laws that govern black holes govern your breathing, your heartbeat, your drifting consciousness. You are safe. You are whole. You are home. Drift now into the deepest layers of rest. Let dreams come if they will, perhaps of orbiting photon spheres or holographic horizons, but do not cling to them. Let them arise and pass like particles flickering at a horizon's edge. Deeper still lies dreamless sleep, the singularity of rest where self dissolves into pure being, where time loses meaning, where you touch the source from which all forms emerge. This is not an ending but a return, not a loss but a homecoming. Like matter becoming part of a black hole's geometry, your consciousness becomes part of sleep's geometry, transformed, not destroyed. In the morning, you will re-emerge with new perspective, refreshed awareness, quiet wisdom gathered in darkness. For now, only rest remains. Only peace. Only the gentle pull of gravity, not toward destruction but toward centering, toward stillness, toward the quiet heart of existence where all paradoxes resolve into harmony. The stars continue their slow dance. Black holes continue their silent spin. The universe continues its expansion. And you, dear listener, continue your journey into rest. Carried on rhythms older than galaxies, cradled in darkness that has witnessed the birth and death of stars, held in a cosmos that is strange and beautiful and fundamentally kind. Let go completely now. Surrender to the night. Become one with the Valerium of sleep, vast, dark, star-dusted, peaceful. Good night.